Hello, welcome to the world of chemistry. This is Dr. Vikram Banchal and I am dealing with spectroscopy and this is lecture number 9. In this lecture, I will explain you Lambert's-Beer's law. In previous lecture, I started what is Lambert's law. This is mainly for sample of different thickness. Normally, when we take sample of a solution, for example like this is a cuvette in which we will fill a solution of particular concentration. Okay, obviously in this solution there are no compartments, but we imagine that there are different compartments of the same thickness. Imagine like this, that the solution is distributed in a different compartments. In fact, it is not like that, but we assume like this. Okay, now the light which passes through this UV visible light, particularly UV visible light, having certain intensity, and that is called I0. This is incident light. As solution has certain amount of concentration, the light which comes out through this will be having different intensity, and that we call it I0, and this light is called transmitted light. And here we have colored solution. So this is colored solution of definite concentration. Okay, and it should be transparent also. So it is colored transparent solution through which the light is passed through. Okay, one thing is very clear, the light which is coming out of this must be monochromatic light. So this must be monochromatic light which is coming out of through filter. Okay, so it has definite wavelength, only one wavelength, and which will come out of this, and now it is passing through a particular solution. Okay, now for that Lambert gave a law which is called Lambert's law, and that is equal fractions of the incident light are absorbed by successive layers of equal thickness of the light absorbing substance. So this is what we call Lambert's law. Now when we write this mathematically, we write like this, that d minus di upon dv is equal to ki. This is known as equation 1, where I will be intensity of light and B is equal to thickness of absorbing substance. So substance can be solid, transparent, or it can be a solution. Okay, it can be solid, transparent, or it can be a solution. Now integrating the first equation, equation 1, we get I is equal to I0 e raised to minus kV. This is equation 2, where I will be intensity of transmitted light, I0 intensity of incident light, K is known as proportionality constant, whose value depends on lambda. Okay, here very important part is this: the intensity of absorbed light will be equals to intensity of incident light minus intensity of transmitted light. Let us call it equation 3. Now I absorbed is equal to I0, substitute the value of I in this, so we write I0 e raised to minus kV, or we can write I0 into 1 minus e raised to minus kV. This is equation number 4. Or we can write I is equal to I0 e raised to minus AB also, where if you compare equation 2 and equation 5, sorry, not here to the base E, but it is to the base 10 raised to minus AB. In that case, K is equal to 2.303A. So on comparing equation 2 and equation 5, we will get this equation. Okay, and this equation is known as Lambert's law. So this is also called Lambert's law. This equation 5 is known as Lambert's law, where A is constant, or A is known as absorptivity. A is known as absorptivity, and B will be thickness. So this is Lambert's law. Now next one is called Beer's law. Again, this is for a solution which is kept in a cuvette of spectrophotometer having certain concentration. Here we assume that it has certain concentration, and that is C. Okay, the light which comes passes through this having definite intensity I0. The light which comes out of this is having different intensity, that is I, transmitted light. Okay, so here we will see that again the law is similar to Beer's law. Let us quote it: equal fractions of the incident light are absorbed by equal changes in concentration of the absorbing substance in a path of constant length. So this is called Beer's law. Again, we represent this law mathematically like this: minus di upon dc, here c stands for concentration, equals to minus k dash I. Okay, this is equation number 6, where c will be concentration of solution. Okay, integrating this equation, integrating equation 6, we will get I is equal to I0 e raised to minus k dash c. This is equation 7. Now, if we combine equation 5 and equation 7, then we have a new equation, that is I is equal to I0 e raised to minus kbc. Okay, or we write I is equal to I0 10 raised to minus abc, or we can write I0, I is equal to I0 10 to the power epsilon bc, where small a is absorptivity and the unit of absorptivity is deciliter per gram per centimeter, and epsilon is molar absorptivity. If we represent concentration in molarity, then we write epsilon, and the unit will be liter, mole inverse, centimeter inverse. Okay, and here B is thickness, C should be concentration. Okay, so this is the equation given by Lambert's-Beer's law, and this equation is called Lambert's-Beer's law. Now, if we go ahead a little bit, then to the base 10, if we remove this, oh sorry, that should be minus, then we can take I upon I0 equals to minus ABC, or I upon I0, sorry, 10 to the power minus ABC, or we can write I upon I0, sorry, instead of that we take this log I upon I0 will be minus ABC, or log I0 upon I equals to ABC. Similarly, log I upon I0 would be minus epsilon BC, or log I0 upon I equals to epsilon BC. This is known as Lambert's-Beer's law. Okay, This is called Lambert's Beer's law.